Hello, everyone, and welcome back to your channel, Basic Engineering. In today's session, I want to go over friction. The topic of friction is very important. We know that friction usually is thought of as a bad thing, right? That you dissipate energy in forms of heat and you are losing efficiency due to friction. But on the other hand, friction is very important to us in life. In fact, it may be a life-saving. Just think about you driving, then all of a sudden you see an object in front of you. You need to brake. If you don't have good coefficient of friction, as we were going to talk about, between your tires and the pavement, it would be a very bad situation. So friction in this case is a good thing. Friction also is a good thing in a machine where you have, you know, like belts that keeps rotating your machine, right? Movable parts. So you want good friction between, the pulleys and the belts, and so on and so forth. So how do we describe friction? How do we use friction? How do we design for friction? Let's take a very simple case. I have a horizontal table or surface, and then I place on top of it a box. Let's say a small box like that. And I ask you, how many forces act on this box? Of course, we have the weight. The weight goes through the center of gravity. Excuse me. And the weight here is the mass times g, Earth acceleration. And because that, in this case, it's a particle, it has to have another, of course, it has to have another force from the sum of the forces in the y equals 0 to be in equilibrium. And that force is the normal force. Normal because it's perpendicular to the surface and it equals mg. And here comes the first fallacy, the first problem that many students have in their mind. They think the weight equals the normal force. No, these are two different, completely different things. And by the way, in fact, N is on the, it's down here. I drew it up, I slid it up so you can see both. But the normal force always occurs between two surfaces because it's an internal force. And how many times so far we said that internal forces always come in pairs. One of them is acting on this box or the crate, and the other one is acting on the surface that is holding um, the plate or the crate. Okay? So we have two equal opposite collinear forces. That's a particle. W equals mg. I'm done. Now, suppose I start pulling, or let's first assume I'm pulling upward like that. So I have a rope and the box is down here. I don't want to stoop and hurt my back, so I attach it to a cord and I pull up. Force F here. Now, all of a sudden, some of the forces in the y equals 0 tells me that N plus the vertical component of the force, both of them add up to mg. So N is less than mg. They don't have to be equal. What if P is down? I'm pulling down. This thing is high and I pull it such that the force I'm pulling with is not horizontal, is inclined down. So now the normal force equals the mg plus a vertical component of that force. So now N is larger than mg. When would N equals mg? Well, as we said, first of all, the crate is resting on a horizontal surface, and if there is an external force acting on the crate, it's also horizontal. Let's call it P. Okay? So now it's still a particle. All the three forces intersect at a point. No rotation. But wait a second, we have a problem here. Do you see it? The sum of the forces in the x doesn't equal zero. So why wouldn't this crate move? You'd say, yeah, if you pull hard enough, it would move. Hard enough. Meaning if your young brother or sister is trying to pull this heavy box, it won't budge, right? So in that case, how is that in equilibrium? Doesn't make any sense. Huh? What? Yes, yes, it's with an F. Friction, yes. But where is the friction? Someone would tell me here, it has to be at the same line so that they cancel each other. Friction in the air? No, friction also, like the normal force, is an internal force. Anything that you don't apply, the only two ways you can have external forces are the weight as well as a force that you apply. Everything else is internal force. And internal forces always come in pairs. They are equal, opposite, collinear. And yes, the friction is tangential to the surface of contact between the box and the surface. So there is another friction going to the right on the surface itself, on the table. Because they are equal and opposite. Like there is a normal force going down on the table. N and N are equal, collinear, and opposite. Excellent, right? P equals F is an equation of a straight line. So if I draw this relationship between P and F, from the sum of the forces in the x equals 0, P equals F. That's an equation of a straight line with a slope of 1 or an angle of 45 degrees. So this angle is 45 degrees, or that slope is 1 to 1. Excellent. Now, P equals F, P equals F. Have you ever tried to help your parents move a heavy stuff without wheels across a room? Think about it, what happened? In the old days, you may even push a car because the battery is dead and we want to start it. If it were a manual shift, right? You won't know that, but your parents will tell you. So when you push in the beginning, it's very hard. I keep pushing this table. Oh my God, it requires a lot of weight, a lot of force. And then all of a sudden I feel that, oh my God, it's about to move. Nice. What is that? This point, when the body is about to move, meaning here there is no motion. But at this point, right there, still P equals F. But we call it the point. Oops, I'm sorry, what is that? Point of impending motion. Motion will occur if you increase the force just slightly. What do you feel when the body you're pushing is start moving? Anyone knows? You feel less resistance. It's easy to keep moving it. But if somebody calls you and say, what? Oh my God, you start again from here. Keep pushing hard, hard, hard until it's about to move. That's the point of impending motion. At this point, and at this point only, all of a sudden, if an equation occurs between F, the friction force, and N, the normal force, what does the normal force have to do with it? Well, at this point, and at this point only, F would equal the normal force times something called mu sub s, or the coefficient of static friction. That's the maximum friction that can occur between the two surfaces, F. Right after this point, you feel the force required, the friction force decreases. And at this point, F would equal N times mu sub K, which is the coefficient of kinetic friction. Mu sub K, mu sub S is greater than mu sub K. So really all what we need to do is to look at this point. If you don't know that you have impending motion, like you are somewhere here, no relationship between F and N. The relationship is between F and P. Okay? So F equals P, F equals P, F equals P. Until this point, still F equals P, but also F at that point equals N times mu sub S. Okay, so now we solve the problem that, first of all, we said the normal force doesn't necessarily equal the weight. P equals F as long as we don't have motion. At the point of impending motion, P equals, or F equals N times mu sub S. Good, so far so good. We still have a problem. Oh my God, this guy is about problems. Yeah, that's my life. I create problems for you. Make it hard. What is the problem? When we started discussing that crate or that box, we refer to it as a particle. We said N and mg are intersecting, they have the same line. And when you align P with that, it has to pass through a point, and that point means that we don't have rotation. But then we thought about friction. What does the P and F? Notice P equals F, it has to be from the summation of the forces in the X. But what did they produce? It's no longer a particle. They don't have the same line of action. So they produce a couple. And this couple wants to tip the box clockwise. So what happens? Why doesn't it tip over? Of course, if it was slender and high, a tall box, and you push it from up there, it would fall down. It would topple, right? But why doesn't this fall down? Or what keeps it from falling down due to this couple? If you draw this couple like that, then definitely this thing is rotating. It keeps moving. What? There's no way. What keeps it from? The only explanation is that once you apply a force, N is no longer collinear with mg. It slides to the right. It's as if the P is pulling N with it. It goes here. If you didn't reach this point, so you have to pull more, N will go more. If N reaches the edge, before P reaches the point of impending motion, then this thing will tip over. Otherwise, if it reaches the maximum force here, then this thing would slide. And we may see an example later that we decide whether the box will slide or tip over. We'll see that. But for now, this is the whole story. We have three equations of equilibrium. Sum of the forces in the x equals 0. Sum of the forces in the y equals 0. And at the point of impending motion, F equals N times mu sub S. Mu sub S would be given to you. And now you can solve for the three unknowns, P, N, and F, or P, or F, N, and mu sub S, depending on the scenario. So you can see now that if I have my box is slender and tall, I have the weight here, and if I apply P so high here, then it produces a humongous moment. If the weight is not large enough, the normal force would reach this point before this restoring moment equates that, and it will tip over. And you can see that makes sense. Even you intuitively, if you are trying to push a heavy box that is slender and tall, either you move it so that this would be the width and that would be the height. And now, even though you had to scoop, but you can move it, or instinctively you'd go down and pull it from down here. If it's still, you pull it from down. You go down to reduce the moment, the tipping moment, so that the restoring moment can resist that. Anyway, that's the whole story really that we need. I prepared an example. I was going to draw the free body diagram, and then I said, wait a second, I have to talk about it first. So I drew anyway. So here we have two masses or two blocks of mass 50 kilogram for this guy and 75 kilogram for that guy. They also tell you that the coefficient of static friction, when they say friction, it means static friction between A and B, as well as between B and the floor, is 0.25, a quarter. We want to determine P, how much force should you push B such that you get impending motion. So now you have two masses on top of each other. We always start with the top, not the bottom. Why? Because the bottom has a normal force, a weight, friction force here, friction force there, a lot of unknowns, and you only have three equations of equilibrium. So the force in the x equals 0, in the y equals 0, and at the point of impending motion, N times mu sub S equals the force. So we draw the free body diagram here, free body diagram of block A, the one on the top. Let's see what we have on the top. First of all, X and Y. Don't forget ever that. It tells you the weight or the mass here is 50. So the weight would be 50 times 9.8. Okay? 490 Newton. What else do we have? We have a normal force going up. We don't have to worry about where to draw it. There is a normal force. There is a friction force at the bottom, but in which direction? Think about it. The friction force, is it to the right or to the left? And how do you know? Mm, what would happen when you push and both blocks want to move to the right? What keeps the top one from going to the right? It's this length that makes an angle of 45 degrees with the horizontal that is pulling it back because it cannot move with the block. So if the block wants to take it and move to the right, this thing is pulling it back like that. With a force, we can call it T for tension, but usually, you can call it F. But I don't want to, no, I don't want to use F to confuse it with friction, even though I use usually lowercase f. But anyway, we are going to call that force F. Okay, it doesn't matter. Or do you think we should call it? Let's call it T because it's a tension. And from here, you see that the friction between A and B has to be to the right from the sum of the forces in the X. And this is 45 degrees. So now, and this is, I'm going to call it A sub F. Because if I call it F, what am I going to call the friction on the bottom one? Okay. And maybe this is A sub N also. Please be careful here. Okay, what equation should we start with? We know, we know that we are at the point of impending motion. We want P that will cause impending motion. So at this point, I can start by saying A sub F equals 0.25 A sub N. So now I only have two unknowns, A sub N and T. A sub F is no longer a force, an unknown. And I have two equations of equilibrium. I can write summation of the forces in the X equals 0. So I get zero point 0.2 or 1/4 A sub N minus T cosine 45 equals 0. Okay, that's one equation. And then I can write summation of the forces in the Y equals 0. I have A sub N plus T sine 45 minus 490, or I can say equals 490 because I was going to say minus 490 equals 0. Giving you an angle of 45 degrees is a lifesaver. Why? Because at 45 degrees, the sine and the cosine equal each other. Nice? Very nice. Meaning, if I add these two equations together, these guys cancel, and I get 5/4 times A sub N equals 490. So I multiply both sides by 4/5 and get A sub N equals 3920 Newton. A sub N is up and A sub F is a quarter of that to the right. So I found A sub N, and of course A sub F is the same direction here, but it's dividing by 4. I get 980 Newton. Okay, I'm done with the top part. Then I move to the bottom, and here you have to be extremely careful. Here is the free body diagram of block B. how many forces act on that? Please remember that A sub n and A sub f are internal forces. They always come in pair. Here is my x and y. Let's see then how many forces. First of all, A sub n is inverted down as A sub n, which is 3920 Newton. A sub f that was going to the right will go here to the left, and it's 980 Newton. So that's what I got from the top crate. These two forces will always be there. I have my P that I want to calculate. It's unknown. I have the weight or the mass here is 75. So I have a weight equal to 75 times 9.8. It's 735 Newton. And finally, I have, no, not finally, I still have something else. B sub F. And finally, I have B sub N. Notice. But it's going up like A sub N. Someone can say, can't I say that since A sub N and B sub N, should I invert both loads and I say 50 plus 75? No, because the force here is the tension. This A sub N, did we get here? Did we do this correctly? How did I get a larger number? This should be 39. Oh my God. Oh, I wrote 4,900. How can it be larger? It doesn't make any sense. Yeah, 392, not 3. Oh my God. This is 392. This is 98. Yeah, notice that 392, it has to be smaller than 490 because the tension here is helping A sub n. So A sub n is less than that. Remember when we said if the forces are either pulling or pushing, then A sub n will not equal the weight. So it's a common mistake that students will say, oh, 50 plus 75 is 125. So the total weight on the bottom one is 125. No, it's not. 125 mass, meaning you multiply it by, no, that's not the mass that is carried. Why? Because this T, this link is carrying part of the 50. It's not all of it 50, but part of it is pulled by T, and A sub n that the bottom block feels is less than 50 kilogram times 9.8. Okay, so now I have everything. I have the two Bn and Bf, and we know that B sub f also equals 0.25 B sub n because I have the same coefficient of friction. And now, and we are at the point of impending motion, so the friction force equals the normal force times the coefficient of friction. And now how many unknowns? I have B sub n, I have B sub f, and I have P. But I use one equation, which is B sub f equals 0.25 B sub n. So to reduce it to two unknowns. If I start with the sum of the forces in the y, notice P is horizontal, I can solve for B sub n right away. So I say summation of the forces in the beginning, I have to say B sub f equals 0.25 B sub n. This is the first equation, like I used it here. And then the second equation would be the sum of the forces in the y equals 0. I have B sub n going up minus 392 going down minus 735 going down equals 0. Nothing else is vertical. So B sub n equals plus 1127 Newton going up. So because B sub F is a quarter of that, I divide by 4 and I get 281.75 Newton, and it's to the left. And finally, I do the summation of the forces in the x direction equals 0. I have P minus B sub F, 281.75, minus A sub F, which is the 98, equals 0. So the force requires to initiate impending motion is 379.75, or roughly 380 Newton. And that's it. So we start always on the top. We write the equation that AF equals A sub n times mu sub s. We write the equations of equilibrium and we solve them, and we invert what we found, A sub n and A sub f, onto the bottom crate. Here A sub n was going up, so I inverted down. This one was going to the right, so I inverted going to the left. And of course, when you push the bottom, it wants to move to the right, so the friction at the bottom is also resisting that by moving to the left. They have to have the same sign, right? Since P is trying to move this block to the right, then the friction on top and the bottom is resisting that. And basically that's it. Okay? I hope this was clear. I'm sorry for this extra zero here. I don't know how I multiply a number by 4/5 and I get it larger, but again, sorry for that. Next time I will prepare a couple of examples to go over. Maybe one would be tricky. So we use inclined surface instead of flat. That's horizontal is quite boring, but as an introduction, I needed to use that. I hope this was easy for you to follow, and I hope to see you soon. Have a great day. Bye.